Okay, here we're continuing practicing with the rules for derivatives of log functions. Of course, now we've got an implicit derivative to compute. So here's what we're asked to compute the derivative of implicitly. It's an equation of x and y, and of course there has to be a logarithm in there somewhere to make it a new problem. And again, you remember the process, I suppose. We just did this in the last section. Take the derivative with respect to x of both sides of the equation. Okay, so 4x cubed plus natural log of y squared plus 2y. We're going to take the derivative of that, and then the derivative of 2x. Okay, so we're just taking the derivative of both sides. You know, we can always look at a logarithm and say, can I simplify that in any way? And I would probably always try to do that, especially when you're taking derivatives. So before I even go any further with derivatives, I might have just done this right away. I have natural log of y squared. And of course, one of those rules we had for logarithms was that if you have natural log of an expression raised to a power, you can actually bring the power out, excuse me, bring it out as a factor. So what I might do here, and I'll go ahead and do it here, I can take that 2 and write it out front as a factor because the expression inside the log was being raised to the power 2. Okay, that was one of our rules in 4.3. Okay, so maybe I'll do that first, but then I go on to the rules of calculus, if I don't see anything else I can simplify, that says, you know, basically when I have a derivative of a sum, I can take the derivative of each term separately. So I've got the derivative of 4x cubed plus the derivative of 2 natural log of y plus the derivative of 2y equals the derivative of 2x. Okay, and again, I say the derivative, but remember we're taking the derivatives with respect to x, which is important here because we have x and y appearing in the equation. Okay, so when you take a derivative with respect to x of the variable itself, or expressions involving it, you know, there's nothing different in implicit differentiation. You know, the derivative of 4x cubed, well, it's 4 times the derivative of x cubed, which is 3x squared, so that'll be like 12x squared. Okay, but over here, you know, we're going to have to spend a little bit more time, just be kind of careful, since we're taking a derivative of a function involving y. Okay, so I can factor the 2 out, and then just take the derivative of natural log of y separately. So maybe I'll go ahead and do that first. And over here, again, I might want to go ahead and factor the 2 out, just so I can focus on that one thing that's different, right, the implicit derivative. Okay, well, the derivative of 2x with respect to x is just 2, so maybe I'll go ahead and do that. By the way, you're always okay jumping ahead, you know, combining some of these steps if you feel comfortable, but I like to go through them a little bit slower in the notes, so on the implicit derivatives, I try to just do one step at a time. Okay, so this first one was done. It's basically 12x squared, okay, plus 2, okay, and then here's the implicit derivative. We're taking the derivative of a natural log of y with respect to x. So it's just that rule for derivative of log of a function. You know, the rule that we had said d dx of natural log of u is the derivative of u over u. Okay, and that's exactly the rule we use here, except instead of u, we've got y. So this derivative is just going to be dy dx over y. Okay, get this rule out of the way. Okay, so next I move on to this term, 2 times the derivative of y with respect to x, which is just dy dx. Okay, so that's where we're at now. And again, from here on out, the process is pretty much the same as any other implicit derivative. We want to solve for that symbol dy dx. So if I maybe I'll rewrite it one more time, just kind of get things in order here. Okay, because we want to take every term that has a dy dx in it and leave it on the left side and probably move this one over to the right side. So I'll subtract 12x squared from both sides. And on the right side now I'll have 2 minus 12x squared. On the left side I just have these two terms, and I can factor dy dx out of both of them. I'll save myself a step here. So that's 2 over y and then plus 2. Okay, So to get the dy dx by itself, I just need to divide both sides by 2 over y plus 2. Okay, so get those to cancel. And let's see, what do I have? I've got, copy it down here, dy dx equals, looks like 2 minus 12x squared over 2 over y plus 2. Okay, a lot of 2's there. Okay, well that's basically the answer. That's the implicit derivative. Probably in the back of the book they wouldn't leave it this way. It's kind of a no-no to leave a fraction within a fraction, so to get rid of this y in the denominator, there's a nice trick we can do. You can always take a fraction and multiply the numerator and denominator by the same thing, and you won't change the whole overall value. So if I multiply the numerator and denominator by y, I'll get dy dx equals, and you see why I chose y now, it's going to cancel this y here. So in the numerator I'll have 2y minus 12x squared y all over, okay, and now look what happens down here. Y times 2 over y is 2, and y times 2 is 2. Okay. So, and then now I'm noticing there's one other thing we can do. We can actually factor a, oops, I'm sorry, it's 2y there. We can actually factor a 2 out of the numerator and denominator and cancel those. So if I factor out a 2 from the numerator, I'll have y minus 6x squared y. In the denominator, I'll have 1 plus y. Okay, and of course these cancel, so finally get a nice answer here. Y minus 6x squared y over 1 plus y. And that is the implicit derivative.